Hello everyone. In this particular video lecture, we are going to study about the CMOS inverter DC characteristics. We know that the CMOS inverter, it is formed by using pMOS and nMOS transistors. The gate of the pMOS and the nMOS transistors are connected, to which input voltage Vin is given. The drain of both pMOS and nMOS are connected, from which the output is going to be taken. The pMOS transistor source is connected to VDD and its substrate or the bulk is connected to VDD. The source of the nMOS is connected to ground and the bulk of the nMOS is connected to ground. So when Vin is equal to 0, pMOS transistor will be on, so that and nMOS transistor is off, causing the output capacitance to charge to VDD. Whereas when Vin is equal to logic 1 or VDD, at that time pMOS transistor will be off and nMOS transistor will be on, causing the output load capacitance to discharge to the ground, or Vout will be equal to 0. That is, whenever the transistor is on, we consider it as a closed switch, and if it is off, we consider it as an open switch. So the current that flows, it depends upon the region of the transistor behavior. We know that the transistor operates in cutoff, linear or saturation region. So the current depends upon the region of operation of the transistor. So for what value of Vin and Vout are this nMOS and pMOS transistors in cutoff, linear or saturation region? That is what we have to find out. So let us consider the nMOS operation. We know that nMOS transistor, it will be in cutoff when the gate to source voltage of the nMOS transistor VGSN is less than VTN, that is the threshold voltage. That means there is no inversion layer formed between the source and the drain, so there is no channel created and no current flows. When VGSN becomes applied is greater than VTN, then the channel is created and current starts flowing when we apply voltage VDS, positive voltage. But VDS, it should be less than VGS minus VTN for the current to be dependent upon the voltage VDSN. But once that is the linear region of operation, because the current is proportional, or we can say that it depends upon the voltage applied between the drain and the source. But once the voltage VDSN becomes greater than VGSN minus VT, then in that case the transistor goes into the saturation region, because this is the point at which VGS minus VT is the voltage at which pinch off would have occurred, and the channel has tapered near the drain. There is no channel formed near the drain because VGD would have become less than VT, and because of this the current no longer depends upon VDS, it is independent of VDS. So the transistor would be in the saturation region. Now this concept, now we are applying it to the nMOS transistor in the CMOS inverter circuit. Now VGS of the nMOS transistor is equal to Vin minus 0. So VGS will be equal to Vin. Similarly, VDS of the nMOS transistor is between the drain and the source. So Vout minus 0. So VDS is equal to Vout. So these things we are going to substitute in the above expressions. So we will get Vin is less than VTN, then the transistor is in cutoff. But when Vin is greater than VTN, then the transistor is on, current starts flowing. When Vout is less than Vin minus VTN, then the transistor is in linear region, and Vout is greater than Vin minus VTN, then the transistor is in saturation region. What did we do? In place of VGS, we have replaced VGS with Vin, VDS with Vout, so that we get these expressions. So Vin less than VTN, the transistor is off. Vin greater than VTN, the transistor is on. Vout less than Vin minus VTN, the transistor is in linear region. Vout greater than Vin minus VTN, the transistor is in saturation region. Similarly, the pMOS transistor, we know that the voltages are opposite to that of the nMOS transistor. So when VGS of the pMOS transistor is greater than VT, then the transistor is in cutoff. But when VGS of the pMOS transistor is less than the threshold voltage, then the transistor is on. VDS is greater than VGS minus VT, it is in linear region, and VDS less than VGS minus VT, it is in the saturation region. Here, when we consider the pMOS transistor in the CMOS inverter circuit, VGS is gate to source voltage. Gate voltage is Vin and source voltage is VDD. So VGS is Vin minus VDD. For pMOS transistor, VTP is negative or it is less than 0. VDS is the voltage between the drain and the source. The drain voltage is Vout and the source voltage is VDD. So VDS is equal to Vout minus VDD. So these values of VGS and VDS we are going to substitute in these expressions so that we get Vin greater than VDD plus VTP, the transistor is off. Vin less than VDD plus VTP, the transistor is on. Vout greater than Vin minus VTP, the transistor is in linear region. Vout less than Vin minus VTP, the transistor is in saturation region. What did we do? In place of VGS, we have put Vin minus VDD. So that minus VDD goes this side. So we get Vin greater than VDD plus VTP or Vin less than VDD plus VTP. Here similarly in place of VDS, we have substituted Vout minus VDD, and in place of VGS, we have substituted Vin minus VDD. So VDD on both sides gets cancelled. So we get Vout greater than Vin minus VTP or Vout less than Vin minus VTP. So next we are going to consider the VI characteristics of both nMOS and pMOS transistors. We know that the VI characteristics of nMOS transistors is in the first quadrant and VI characteristics of the pMOS transistor are in the third quadrant, because for the pMOS transistor the voltage VDS and the current IDS are negative. Now we need to bring the graph of the pMOS transistor to the second quadrant and then map it to the first quadrant. Then we need to take the points where both the characteristics are going to meet. Those points have to be plotted to get the characteristics of the CMOS inverter circuit. So let us consider this example where VGS is -1 or -2.5 for the pMOS characteristics here we have drawn. So next we try to translate it to the second quadrant by taking Vin is equal to VDD plus VGSP. So when Vin is equal to VDD plus VGSP, we get Vin is equal to 0 or Vin is equal to 1.5. And then we translate this to the first quadrant here. So you can see translating to the first quadrant, we are moving this to the first quadrant, so you get the characteristics in this manner. Here we have considered VDD is equal to 2.5 volts. So when the green color shows the VI characteristics of the nMOS transistor, the blue color shows the characteristics of the pMOS transistor. Now the points where the graphs are going to meet have to be taken into consideration, and then the characteristics of the CMOS inverter is going to be drawn. So Vin is equal to 1, Vin1 of nMOS and Vin1 of pMOS are going to be taken, and the point of intersections are going to be noted. So it is as if we consider here in this particular case Vin is equal to 0. So when Vin is equal to 0, the 0 point has been mapped. Similarly, Vin is equal to 0.2, slightly greater than 0. Next, Vin is equal to 0.4 VDD the intersection point has been taken. Vin is equal to 0.6 VDD, the intersection point has been taken. Similarly, Vin is equal to 0.8 VDD and Vin is equal to VDD. So all the intersection points are going to be taken, and these points are going to be now mapped onto Vin versus Vout plot. So when Vin versus Vout plot, in that we are going to map the intersection points, the graph which we get will be in this particular manner. Now, when we get the DC characteristics or the transfer curve of the CMOS inverter circuit, we have seen here that when the input voltage is 0 and less than the threshold voltage of the nMOS transistor, you can see the nMOS transistor is off or the pMOS transistor would be on, causing the output voltage to be logic 1. Now, as the input voltage increases, the output voltage is gradually decreasing, and when the input voltage becomes VDD, the output voltage becomes 0. Because at this particular point, nMOS transistor is on, pMOS transistor is off, and the output load capacitance would discharge to logic 0. So, the DC transfer characteristics or the voltage transfer characteristics of the CMOS inverter indicates that when the input voltage is logic 0, at that time output voltage is logic 1, and when the input voltage is logic 1, output voltage is logic 0. So here in this particular case, when does the current flow through the CMOS inverter circuit? You can see here that when the input given to the CMOS inverter is varying from 0 to VDD, at that particular point there is some voltage at which both the pMOS and nMOS transistors are conducting, and when both nMOS and pMOS transistors are conducting, the current flows between VDD and ground. Otherwise, if pMOS is off or nMOS is off, there is no path for the current to flow between VDD and ground. Thus, the point where both the transistors are on, at that point the current flows between VDD and ground, and we can see that there is a shoot up of the current between VDD and ground only at one particular point on the characteristics. So, based on the basic concept, like the conditions when the pMOS and nMOS transistors are in cutoff, linear and saturation region, we come to know that in which region of operation the transistors, pMOS and nMOS transistors are in this A, B, C, D, E regions. Region A, in region A, the nMOS transistor, you can see the input voltage is less than VTN. So, when the input voltage is less than the threshold voltage of the nMOS transistor, then the nMOS transistor is off, because the input voltage, that is the gate voltage given to the nMOS transistor, is less than the threshold voltage. So, nMOS transistor will be in the cutoff region. Similarly, as the input voltage increases, once the input voltage is greater than VTN, then in the region B, the nMOS transistor is in the saturation region. Region C also, nMOS transistor is in saturation region. Similarly, region D and E, it goes to linear region. Similarly, pMOS transistor in E region, it is cut off because the input voltage is VDD. And D and C region, the pMOS is in saturation region. A and B, it is in linear region. We will try to see that whatever region of operations we have just now analyzed or indicated are true. Now, region A, Vin is less than VTN, so nMOS transistor is off or it will be in cutoff region. Now here, if Vout is greater than Vin minus VTP, this is the condition for pMOS to be in the linear region. Now this condition satisfies, then we say that the pMOS is in the linear region. Now, because nMOS transistor is off, the total current flowing between the VDD and ground is equal to 0. So when current flowing is equal to 0, then the drain to source voltage of the pMOS transistor will be equal to 0 because there is no current flowing. But VDSP, that is drain to source voltage of pMOS transistor, it is given by Vout minus VDD because drain voltage is Vout and source voltage is VDD for pMOS transistor. So Vout minus VDD is equal to 0 or Vout is equal to VDD. Now Vout is equal to VDD, it satisfies this condition that VDD is greater than Vin minus VTP. Because here Vin is almost equal to 0. So VDD is greater than almost some value which is nearer to 0. So because this condition holds good, pMOS transistor will be in the linear region. Now in region B, the region B is between, when the input is between VTN and VDD by 2. Now we consider the condition Vout greater than Vin minus VTN. Now when we consider the point Vout will be slightly less than VDD. So we have considered Vout as VDD minus delta because it is slightly less than VDD. Vin, we have taken a point which is slightly less than VDD by 2. So Vin is replaced with VDD by 2 minus delta and we have minus VTN. So obviously from this expression we know that VDD minus delta will be greater than VDD by 2 minus delta minus VTN. This is true. So because the condition Vout greater than Vin minus VTN is satisfied, we say the nMOS transistor will be in saturation region. Now consider the condition Vout greater than Vin minus VTP. Vout, as I told you, it is VDD minus delta because it is slightly less than VDD, and Vin we have considered VDD by 2 minus delta minus VTP. Once again this condition holds good. So we say that the pMOS transistor is in linear region in the region B. So region A, nMOS transistor is cut off, pMOS transistor is in linear region. Region B, nMOS is in saturation region and pMOS is in linear region. Consider region C. Region C is nothing but the point where input voltage is equal to VDD by 2. Now consider Vout greater than Vin minus VTN. Again the same condition. So Vout will be equal to VDD by 2. So that is the point at which Vin is equal to VDD by 2, Vout is equal to VDD by 2 and the threshold voltage of the CMOS inverter is also equal to VDD by 2. So Vout we write it as VDD by 2, Vin also we substitute VDD by 2. So from this expression we come to know VDD by 2 is greater than VDD by 2 minus VTN. Why it is greater? Because VTN is a positive value. So condition holds good and obviously nMOS transistor is in saturation region. Consider the condition Vout less than Vin minus VTP for pMOS transistor. Once again substitute Vout is equal to VDD by 2 and Vin is equal to VDD by 2. So from this condition holds good. Why? Because VTP is a negative value. So VDD by 2 minus of some value will be VDD by 2 plus something. So obviously the right hand side will be greater than the left hand side. Now because this condition holds good, the pMOS transistor is in saturation region. So you can see that in region C, both nMOS and pMOS transistors are in saturation region. Now when the transistors are in saturation region, in region C, we equate the currents of both nMOS and pMOS transistor in the saturation region. The nMOS transistor saturation current is beta n by 2 VGS minus VT by whole square, where VGS we have replaced it with Vin. Similarly for IDSP, that is the current flowing through pMOS transistor is beta P by 2 into VGSP minus VTP whole square. But VGSP, that is gate to source voltage of pMOS transistor, it is given by Vin minus VDD. So we substitute. So here in this particular case, IDSP, it is negative value because IDSP it is drain to source current, but actually holds or the current through PMOS transistor flows from source to drain. So that's why we consider the negative sign. Now IDSN is equal to minus IDSP, so that we get this minus of minus becomes plus here, and we have equated both the currents. Now in this expression Vin minus VDD minus VTP, I have taken minus out, minus common, so that I get minus of minus Vin plus VDD plus VTP whole square. But because it is whole square, this minus into minus becomes plus. Now beta n by beta p into Vin minus Vtn whole square is equal to minus Vin plus VDD plus VTP whole square. Or when we solve this expression by taking the square root on both the sides, we get Vin is equal to VDD plus VTP plus Vtn square root of beta n by beta p by 1 plus square root of beta n by beta p. So this is the expression for Vin in case of the nMOS and pMOS transistor in saturation region, that is region C. And as I have told you, Vin is equal to Vout is equal to threshold voltage of the inverter in region C. Now in region D, the region D is considered when the input voltage is between VDD by 2 and VDD plus VTP. When Vin ranges between these two voltages, then it is region D. Now we consider the condition Vout less than Vin minus Vtn. So when region D occurs, we know that the output is almost nearer to 0. So we take Vout is equal to 0 plus delta, and Vin is VDD minus delta. So we substitute Vout and VDD values. So from the expression we know that right hand side is greater than left hand side, which is true. So nMOS transistor is in linear region. Similarly, when we consider the condition Vout less than Vin minus VTP for the pMOS transistor, once again we substitute the values of Vout and Vin, and we come to know that the right hand side is greater than the left hand side. So pMOS transistor is in saturation region. So in region D, the nMOS is in linear region and pMOS is in saturation region. Now region E is the condition where Vin is greater than VDD plus VTP. So when Vin is greater than VDD plus VTP, from this VGSP will be greater than VTP, which VGSP it is gate to source voltage of the pMOS transistor, which is Vin minus VDD. So Vin minus VDD, it is greater than VTP. So that is the condition, Vin greater than VDD plus VTP, or Vin minus VDD greater than VTP, that is VGSP greater than VTP. But if VGSP is greater than VTP, then the pMOS transistor is off. Because for the pMOS to be on, VGSP should be less than VTP. So because the pMOS is off, the current flowing is equal to 0. So drain to source voltage of the nMOS transistor which is conducting will be equal to 0. But drain to source voltage is equal to Vout. So Vout will be equal to 0. So when Vout is equal to 0, Vout less than Vin minus Vtn condition holds good, and nMOS transistor is in linear region. So what did we understand? Region E, the pMOS is off, that is it is in the cutoff region, and nMOS, it is in the linear region. So in region A is between when the input is between 0 to Vtn, pMOS is fully on and the nMOS is fully off, no current is flowing, and output is equal to VDD. In region B, the input voltage has increased and it is input voltage ranges between Vtn and VDD by 2. Both nMOS and pMOS are on. The nMOS, it conducts large voltage, it is in saturation. pMOS is conducting small voltage, so it will be in resistive or linear region, and small amount of current flows between VDD and VSS. But once region C occurs, that is V in is equal to VDD by 2, then V out also will be equal to VDD by 2. Both the transistors pMOS and nMOS are in the saturation region and large amount of current flows between VDD and the ground. So that is the point at which peak current flows between VDD and ground in the CMOS inverter circuit. Region D, pMOS is off and nMOS is on and in the linear region. This region occurs when V in, as I told you, is greater than VDD plus VTP. Now let us study about what is skewed and unskewed inverter circuit. Now skewed or unskewed inverter circuit we will study or analyze based on the beta or the device transconductance of pMOS and nMOS. So consider the case where beta P is equal to beta N. We know beta is given by mu COX W by L. So L, that is the length of the gate or length of the channel, it depends upon the process technology which is used for the fabrication. So Ln is equal to Lp. Beta n is given by mu n COX W by L of nMOS. Beta P is given by mu P COX W by L of pMOS transistor. So when beta P by beta n is considered, it is equal to mu P WP by mu n Wn, or W by L of pMOS transistor will be equal to 2.5 times W by L of the nMOS transistor, because mu n is equal to 2.5 mu P. So the ratio beta P by beta n is 1 when the width of the pMOS transistor is equal to 2.5 times the width of the nMOS transistor, and at that time the inverter threshold voltage will be equal to VDD by 2. So CMOS inverter drives a capacitive load, and both the pMOS and nMOS transistors, they charge and discharge in equal times, meaning that the inverter has equal sourcing and sinking capabilities to the load. So the charging time of the capacitive load and discharging time of the capacitive load are equal, because beta P is considered equal to beta N, and that happens when width of pMOS transistor is equal to 2.5 times the width of the nMOS transistor. But now consider the case where beta P is not equal to beta N. Now in this case we call the transistor as skewed inverter circuit. When beta P was equal to beta N, the transistor was unskewed inverter. That is, the ratio beta P by beta N is equal to 1. It was unskewed inverter. But when beta P is not equal to beta N, then we call it as a skewed inverter. Now in this instance, the beta value for one of the transistors would be greater than the other. That means the transistor which has beta value larger will become stronger, and it will have greater load driving capabilities. So when beta P is greater than beta N, then beta P by beta N will be greater than 1, and we call it as high skewed inverter. Whereas if beta N is greater than beta P, then beta P by beta N will be less than 1, and we call it as the low skewed inverter. When beta N is equal to beta P, or beta P by beta N is equal to 1, we call it as an unskewed inverter circuit. So in high skewed inverter, the pMOS transistor is stronger, so the input threshold voltage is greater than that of the unskewed inverter. Hence the output voltage is greater than VDD by 2, and this is characterized by rightward movement of the inverter transfer characteristics. So in a high skewed inverter, the transfer characteristics would move towards the right of the characteristics when beta P equal to beta N. The converse is true for low skewed inverter, that is the one which has weaker pMOS transistor. So the input threshold voltage is lower, so it will lead to lower output voltage, the output voltage less than VDD by 2. So the inverter transfer characteristics would move towards the left of the characteristics when beta P is equal to beta N. And finally, from practical perspective, width variable of beta is often used to skew the beta ratio because it maintains minimum length, which is critical for speed. So you can see here that when beta p equal to beta n, we have certain DC characteristics, but when beta p by beta n becomes greater than 1, you can see the characteristics move towards the right. Beta p by beta n less than 1, then the characteristics move towards the left. So when beta p is not equal to beta n, we call that as skewed gate or skewed inverter. So next we will study about the logic levels. Now let us consider this circuit where one inverter is driving another inverter. So we have 3 inverters here. Output of each inverter is driving the next inverter. And we have considered the wire connecting the output of one inverter to the input of another inverter. We have shown here it as interconnect. So this interconnect is connecting the output of one gate to the input of the other gate. Now VOH is the voltage applied, that is logic 1 is the voltage applied at the input of the first inverter. So logic 0 or VOL is the voltage which we get at the output of the first inverter. So this logic 0 or VOL has to be transmitted through this particular interconnect to the input of the next NOT gate. So this interconnect, because it is a wire connecting the output of the first gate to the input of the second gate, noise would be added to the signal which is being transmitted. Because of that, the voltage VOL has now become VIL. The voltage VOL has now become VIL. And this VIL, when given as input to this gate, should give me VOH. That means I had given logic 1, I got logic 0. This logic 0 was transmitted through the interconnect. Still the signal should be logic 0 at the input of the gate, so that it gives me logic 1, and that when transmitted again should be logic 1 that would be given to the input of the next gate, and I should get logic 0. So whatever voltage VIL I am going to get after VOL is being transmitted through the interconnect, that voltage will be the maximum allowable voltage that is considered as logic 0. Now beyond this point, if the voltage has been corrupted by noise and changed, then it will not be considered as logic 0. Similarly, the logic 1 signal, which is VOH, and it is getting transmitted through this interconnect, and once it reaches the input of the third gate, that is considered as VIH. Now that means it is corrupted by VOH is corrupted by noise and has become VIH, but still it has to be logic 1 so that the output which we get from the inverter is logic 0. So this is VIH is the minimum allowable voltage that will be considered as logic 1. So the characteristics, whatever the DC characteristics of the VTC, that is voltage transfer characteristics of the inverter we have, from that on that we have marked VOL, VOH, VIL and VIH. So here VIL and VIH are the input low voltage and input high voltage at which the slope of the characteristics is -1. So VIL, input voltage you project to the characteristics, that is like this is the point at which the slope is equal to -1. So that the point at which slope is equal to -1 you project, that input voltage is VIL. Similarly, one more point at which the slope is equal to -1 when you project, that is VIH. So this first point where the slope is equal to -1, slope of the DC characteristics is equal to -1, the input voltage is VIL, output voltage is VOH. And the second point, VIH and VOL. So VIH and VIL are the input low voltage and input high voltage at which the slope of the characteristics is -1. VIL is the maximum allowable voltage at which the input we consider it as logic which will produce logic 1 output, or it is the maximum allowable voltage which is considered as logic 0. Similarly, VIH is the minimum allowable voltage at which the input is high enough to ensure logic 0 output, or we can say that VIH is the minimum allowable voltage which will be considered as logic 1. So from this we have 5 critical voltage which characterize the DC characteristics of the CMOS inverter. VOH is the maximum output voltage when the output level is logic 1. VOL is the minimum output voltage considered as logic 0. VIL is the maximum input voltage considered as logic 0. VIH is the minimum input voltage considered as logic 1. Sorry, this is logic 1. So this is the minimum voltage considered as logic 1. The VTH is the inverter threshold voltage. It is a transition voltage at which Vin is equal to Vout on the VTC curve. That is the region C. As I told you, Vin is equal to that is the point at which Vin is equal to Vout is equal to VDD by 2, and it is equal to the threshold voltage of the inverter. Noise margin. From this particular input and output we have marked here. So the output ranges from 0, this is 0, to VDD, and we have VOH and we have VOL. So 0 to VOL is considered as logic 0, VOH to VDD is considered as logic 1 or logic high output range. Similarly, you can see the input characteristic here. Input, we have 0 to VIL, that is considered as logic 0, and VIH to VDD is considered as logic 1. So here in this particular case, the noise margin, high noise margin nMH will be equal to VOH minus VIH, and nML, low noise margin, that is noise margin at low signal levels, is VIL minus VOL. So what is noise margin? It is the noise tolerance for the digital circuit, and noise immunity increases with the noise margin. It is the amount of variations in the signal levels that can be allowed while the signal is transmitted from output of one gate to input of the next gate. So that is what I had explained you. Through the interconnect, when the signal is being transmitted, even though it has been corrupted by the noise, the logic 1 signal remains logic 1 or logic 0 signal remains logic 0. So that much noise immunity or noise margin is present. But beyond that, if it gets corrupted, then obviously the logic levels of the input signal would change. So noise margin is the amount of variations in the signal levels that can be allowed while the signal is transmitted from output of one gate to input of the next gate. So to maximize the noise margin, the logic levels should be selected at unity gain point of the DC characteristic, DC transfer characteristic, that is unity gain occurs at slope is equal to -1. So the noise margin for high signal levels, that is nMH is equal to VOH minus VIH, and for low signal levels nML is equal to VIL minus VOL. So we have completed the topic DC characteristics of the CMOS inverter circuit. I hope you have enjoyed the lecture. Thank you. Please like and subscribe.